Laura Bush, the editorial director of Spectroscopy, and I'm here today with Ralph Sturgeon of the National Research Council Canada. Dr. Sturgeon, thank you for joining us today.
Well, good afternoon, Laura, and it's certainly my pleasure. Thank you for inviting me.
So sample introduction has been called the Achilles heel of atomic spectroscopy. Is that still the case? And if so, will it always be true?
I think that it really will remain a weakness, but obviously, unfortunately for all of us, it's by no means fatal, as it was for Achilles. Browner and Bourne's paper, which came out in Analytical Chemistry many years ago, has frequently been cited innumerable times when it comes to this kind of situation. The premise behind it was that the goal of sample introduction was the reproducible transfer of a representative portion of the sample material to the atomizer cell with high efficiency and no adverse interference effects. So we can see there's some latitude for interpreting what do you really mean by high efficiency, and when does it really become evident that the interferences are actually adverse. Now, they conclude themselves in that article, if you go back and look at it, that there was a qualified yes, that sample introduction is the Achilles heel of atomic spectroscopy, but they qualified it at the time because they felt that there were some significant advancements on the horizon that were being made that would improve things in the future. And I think we see the fruits of those labors today. We see a huge variety of nebulizers that are currently available that have developed over the last 25 years. We see different interfaces that have been optimized for different sampling devices, etc. And interferences associated with sample introduction stage, though, I think they're still there from the classical solution nebulization technique right through to those people who are using laser ablation for solid sampling. The one thing that stands out differently today, though, is that all of these techniques, I think, are better understood, and in some specific cases they can be remediated. The initial weakness in sample introduction approaches, as I mentioned, stems from a basic lack of understanding and theory of modeling of these systems. But we see that there's been an inordinate amount of work in the past decade on solvent plasma, vapor plasma, and aerosol plasma interactions by people such as John Olisic and Sam Houck, Gary Hefia, Akbar Montaser, Detlef Günther, Jean-Michel Mermet, Animi Bogarts, and the list goes on and on. They've begun to unravel some of the complexities of these processes and the critical role that each of them plays. And so there's a variety of commercial systems out there for sample introduction strategies now available, and many of them have overcome some very specific application-oriented problems. And we can cite examples of that, such as dedicated GC ICP-MS sample introduction lines, or the very difficult capillary electrophoresis ICP-MS lines. And there are a number of benefits that even accrue from the development of flow injection techniques, which covers a wide variety of sampling areas. And even the more recent developments for laser ablation with particular laser ablation operating parameters, femtosecond ablation in the UV, etc., and even some of these large open to the atmosphere gas exchange sampling devices for the laser ablation aerosols. But if we go back and look at this thing from another perspective, such as Gary Hefia likes to do, where he often starts to summarize what are the ideal characteristics we're looking for in a device, and then contrast these with what we actually have as the current characteristics in the laboratory. And you can see there's shortcomings with just about every sample introduction approach that we still have. Moreover, it's evident that the problem rests not entirely with the sample introduction device itself, but it's also inextricably linked to the atomic spectroscopy source. And that doesn't matter whether it's the atomic emission, absorption, fluorescence, or mass spectrometry. And circumventing the shortcomings of the sample introduction device, such as a pneumatic nebulizer, really just transfers some of the problem to the source itself. So if we can increase the efficiency of sampling with a pneumatic nebulizer, for example, from its current level of around 2% up to 40, 50, or 100%, we're transferring the problem to the source itself, because every time you have an energy-limited atomic spectroscopy source, it's inevitable that that's going to lead to some kind of physical or spectral interferences. So the solution at present, for what I can suggest, is that and I don't really mean this to be adopted, is that we dissolve all the samples. We put everything into solution, and that way we can get homogeneity, so we'll have a representative fraction for sampling. And then further, we could remove all the other concomitants from the sample solution and effect a pre-concentration of the analyte itself, and then do calibration using standards. Obviously, very few people are going to bother doing that because it's just not cost-effective from a throughput perspective. So I think I'd summarize in saying to you that I wouldn't want to predict the future more than anyone else would, but I could say that sample introduction is probably not the Achilles heel of atomic spectroscopy, because we have a very powerful array of different instrumentation for elemental analysis that has sufficient detection power to meet most of the needs for analysis at this time. But I think when you really look at it, we're roadblocked from a number of other avenues, and that is sample preparation itself and contamination control. So we need to control the size of our blanks as we go to ever lower demands for analysis. But every year there's developments in these areas, and we've yet to reach these ideal goals of representative sampling, 100% sample efficiency with no interferences. But this might likely arise as a consequence of developments in all three areas, that is sample introduction, improvements to the instrumentation itself, and in sample preparation. So we need to really consider all three, and I don't think we can answer this question in isolation as to whether sample introduction itself is the Achilles heel to atomic spectroscopy.
Some of your recent work has focused on UV photogeneration as a sample introduction system. Can this technique be applied to the majority of elements in the periodic table? And is it a multi-element or a single-element approach?
That's a great question. I love it because that's what I'm currently working on. Most of my effort goes into that right now. Vapor generation of specific analytes does provide us with a means of circumventing a number of the problems that we spoke about earlier with regards to the first question relating to sample introduction. But unfortunately, vapor generation is just not something which can be applied to the majority of elements in the periodic table. When it can be applied, it's possible to do so with a 100% generation efficiency, which makes our sample introduction efficiency very high, and it can also be done with basically no adverse interference effects. But as I say, it's not applicable to all elements in the periodic table, but if you look at the literature over the last 10 to 15 years, there's been a lot of effort in the international community which has significantly expanded the actual suite of elements that are amenable to vapor generation techniques. And in normal circumstances, conditions can usually be established with vapor generation to yield a multi-element detection capability. So you can get 4, 5, or 6 elements in the same chemical manifold to generate a vapor form and have high efficiency. But we have to realize that we're dealing here now with the chemistry of the vapor generation system and not the physics of a mechanical sample introduction system. So as a consequence, vapor generation is always going to be more element specific, but we can have compromised chemical conditions that are sometimes readily available to do 5 or 6 elements at a time. But typically, you're optimizing for 1 or 2, primarily 1 element at a time. I should say that in the context of UV photogeneration, this complements other existing vapor generation techniques, because you have to realize there's a wide variety of vapor generation techniques in current use today, and that includes hydride generation, alkylation, cold vapor generation, which is usually attributed to mercury and cadmium, formation of volatile metal chelates, and even halide generation. But there's different chemistry involved in each case, and that tends to limit its application to a small suite of elements. But it does now include the transition metals and some anions, which conventional vapor generation clearly was not able to access. But since it's a relatively new area, we've only been doing this, when I say new, we've been doing this for about 10 years now. But a lot remains to be explored yet, including just how many elements can be tackled and what the potential problems might be when we start looking at real systems and considering interferences from other concomitants in the sample. Those are questions that have yet to be addressed.
This concludes part 1 of the interview. To hear Ralph Sturgeon's views on speciation, isotope analysis, and nanomaterial analysis, listen to part 2.